Recall the circular definition of the sine and cosine functions. Sine being the x-coordinate, the cosine the y-coordinate of a point on a unit circle at angle theta from the x-axis. If we look at a triangle, let's say this triangle, then this leg of the triangle is the cosine of theta, this leg is the sine of theta. When we add the squares of these two legs, we get the square of the hypotenuse. Since the hypotenuse is 1, its square is 1, therefore cosine squared theta, square of this leg, plus sine squared theta, the square of this leg, equals 1 squared, or just 1, and we say that sine squared theta plus cosine squared theta equals 1. This is true for any angle theta. We can also see this again simply in terms of a triangle. Hypotenuse 1, we have cosine theta here, sine theta here, where theta is implicitly the angle in the lower left-hand corner. And again, the Pythagorean theorem tells us this identity. So we call this the Pythagorean identity. If we look at the graph of y equals sine x, a graph that we're used to drawing, we see that, of course, the graph ranges in value from -1 to 1. That is, y ranges from -1 to 1 for all values of x. If we recall the way the sine function starts, if you remember the circular function, we start at 0, and we're going counterclockwise in the circle, so we go up, then down, then up. Okay, at this point, we're going up here, we're going down if we go to the other side. That is, if we rotate it backwards, we go down like this. It should be clear from your knowledge of the graph that if we take any value of x here and project over, we of course get the sine of x. Now if we take the value negative x and project, we're going to have to go down. If we went up here, we go down here to get the sine of negative x. And this hump here is perfectly reflected through the origin in this hump here, so that the sine of negative x is just the negative of the sine of x. And this is called a reflection identity. This will of course be true for any x. You go out some distance in this direction, then you go back the same distance in this direction, you're just going to get the negative of the value of the sine. That is, the y-coordinate, if you go a distance in this direction, will be the negative of the y-coordinate if you'd gone the same distance in this direction. And we say then that sine of x equals a negative sine of negative x. That's our reflection identity for the sine function. And it just follows from the fact that the sine is an odd function. That is, when you go back this way, it starts moving in the opposite direction as if you go this way. It starts moving positive here and negative when you go in this direction. The cosine, on the other hand, is what's called an even function. It starts at a peak, and any distance you move along here, the reflection over here is going to have exactly the same value. If you move a distance x here and project downward, you'll get the value y equals cosine x. If you move the same distance in the negative x direction, you're going to get the same value for the cosine, so that the cosine of x is the same as the cosine of negative x. And in this case, we say that our reflection identity looks like this. Cosine of negative x is the same as the cosine of x.